So after drawing Lewis structures, our next LO would be to know, or probably to we can identify polarity. So identifying polarity, meaning we can tell if a substance is polar and not polar. So there are actually uh, two basic idea in knowing uh, what the polarity of a particular substance. We need the polarity of substance because this determines whether a particular compound can be dissolved in a solution. So actually, our this chapter two, the LP2 that we were discussing is about solids and liquids. So basically, we will be discussing solids and liquids pertaining to the next chapter also, which is solutions. So it's so important because what makes up a solution, of course, just like the water at sea, because you're a marine biologist, you will be a marine biologist, you should know that there are solids that are dissolved in liquids or probably liquids also, and that's the main thing. So we have already talked about ionic substances, and they do split some of them, if the bond between ionic substances can be broken up by the polarity of the water, therefore we can say that those ionic substances can be dissolved. There's a deeper chemistry for that, but for us, I only taught you how to use your table of ionic substances. So you should use, or you should know how to use tables for ionic substances, which are the double bond, the single, I mean the single ions charge, two charges, and then you should have the table of dissolutions. Of course, the complicated uh, theory of it would, I think, come to the last topics, which is acids and base, and then you have your equilibrium. So anyway, I just taught you how to use those tables. Anyway, so since this is the topic of solids and liquids, we'll be discussing about liquids. So the first topic is of course polarity, or the next topic from the Lewis structures is polarity. So you should know how to identify the polarity of a particular substance. So that's the LO. LO is identify the polarity, identifying polarity, meaning we can tell if a substance is uh, probably polar or not, identifying, or in other way around, we can say that one substance can dissolve probably in another substance. So if usually the water is usually the solvent, so we can tell if a particular substance can dissolve in water or not. So that subject is polarity. So identifying polarity, there are two ways to look at this. First is you have to look at the bond. Bond is uh, of course, polarity as a bond. So we go to the basic of them. Uh, what we're talking is non-covalent substances. So as we reviewed, you already know how to identify non-covalent substances. They are the substances that is formed from non-metals, from the right side of the periodic table. Let's say you have oxygen. So oxygen is a is a covalent substance, meaning it is made up of non-metals. So oxygen, as you can draw them in terms of polarity, um, uh, this diatomic substance, we call this diatomic because it contains two atoms, O2 and 2. These diatomic substances are usually non-polar. Non-polar O2 and 2, you have um, uh, H2. Yes, hydrogen is considered non-metal even though it is listed somewhat on the left, but because it's also a non-metal. H2 and 2O2, you have, I think you also have S2, S8. But anyway, you can imagine that since the bond between them is so even, so the same, I mean from one side to the other, so you can say that they are non-polar compared to their counterparts, um let's say OH. OH. OH would be a nonpolar compared to H2 compared to H2 and O2. This is also the atomic substance, but you can see that OH is nonpolar. Why? Because the bond is not the same. So you can imagine you have oxygen and you have a bond of oxygen and hydrogen. So you can see the way we imagine this is because of electronegativity. So your periodic table has electronegativity with it. You just look at the periodic table and you can see that there is electronegativity with that. Anyway, I can probably pause, find a table with electronegativity. Excuse. So this is a table of electronegativity. Your periodic table has a similar like this. They may have different number in the range of, let's say this would be a 3.4 or 3.6. It doesn't matter. It's just that is not really that accurate. As you can see, the last number is not that accurate when we discussed about significant figures. So 3.5, 3.6, 3.4 doesn't matter. So as you can see, oxygen has a 3.5 while hydrogen has a 2.1. So you only have to take the difference between between electronegativity, and now you can already predict if that particular compound is polar or not. And this is for diatomic substances. These rules, when you look at the bond, it only pertains about diatomic substances. So probably you're only considering two atoms, the polarity between two atoms that is in contact. So that is the thought of this. So if you have oxygen, which is 3.5, uh, 3.5, and then your hydrogen is a 2.1, I think that's a 2.1. So you can see again what is electronegativity. Electronegativity, as you can see the definitions required for us to really read those terms. I've already read many times. I'm already an instructor, but I'm still reading it. So it's really surprising for me that you're not reading your book since you're a student. Anyway, again, the definition of your electronegativity is the ability of that particular atom to attract or to make those valence electrons, all the valence electrons nearby, meaning for this case, oxygen and hydrogen, to really be pulled to that particular atom. So since oxygen has a bigger electronegativity, it means that all these atoms that's being shared, since hydrogen has already no atoms left, and all those electrons left, and all those electrons left from the oxygen, since it will still carry those six electrons, six, because I think you have still have one here. That's why it's at a negatively bond, negatively charged. I think I will just extract how to get this charge because that is formal charge. Anyway, our LO now is to identify polarity. Maybe I'll just make a video about that. So it would now all these electrons would somehow delve or somehow um, stay with oxygen and not really from hydrogen. So we say that this substance is a polar one, meaning this would be a negatively charged part while this one is a positively charged part. Usually you draw the polarity in terms of like this, a positively part, and this would be a negative part. So that's why we call it polarity, because the poles now of the positive, like just like a magnet, the negative pole and the positive pole are now seen. Unlike for oxygen, if you have two oxygen here, of course, since they have the same, I can't remember if the bond is double bond or single bond. Um, maybe double bond. I'm not that sure because of course we have to look go back and we'll be discussing it again. But anyway, if this would be the case for your oxygen, so you can see that all these atoms would be shared equally. Again, that's the thought. Sharing of the electrons equally. So if that those atoms is sharing those electrons equally, meaning all these electrons nearby would just dwell probably on the other side at equal probability, then we say that this substance is non-polar. Okay? So that's why all those diatomic substances are non-polar because it has equal sharing and equal capability. If this is a 3.5 electronegativity, this is also a 3.5 electronegativity. So if we minus that or we subtract that, you would have an electronegativity difference which is zero. So a zero electronegativity difference is a tantamount of saying that that substance has no positive and negative charge that is seen as a whole. So we say that that substance or those substances are non-polar compared to this substance which is polar. So we go back to your water. Water has, of course, this is a bit complicated because there are two hydrogens. But you can see that for every bond, oxygen and hydrogen, of course, this is also the part. Oxygen would be owing all those electrons, this shared and even the non-shared, would uh, almost be with oxygen. And electrons would just be a little bit, sometimes go to the hydrogen part. But usually in drawing, oh, it looks like a cat now. In drawing, we can say that these electrons live its most of its life in the area of oxygen. So this would part here would be a negative part because that's where the part where electrons are, and this part here would be a positively charged. So even though this is equivalent substances, meaning they are not charged substances, unlike the ionic substances, but we can say that covalent substances may have some charges, inherent charges because of polarity. So that's what makes polarity an important matter. 'Di ba? We first discussed the ionic substances because they really has charge, but non-covalent substances when say they don't have charges, they have sharing electrons, but now it seems that some of them has charges. The way you to represent it is of course polarity in terms of bonds. So that is the first one when we discuss polarity. We just go to periodic table, minus or take the difference of the electronegativity. Again, that term negativity, it is found in the periodic table. And then if you minus it, if you subtract it, the more it is near from zero, the more it is nonpolar. So basically, all the substances, diatomic substances, is nonpolar because they would have zero electronegativity difference. Okay? So, and then the more you have numbers from zero, the more it becomes a polar substance, just like water, probably. So that's the first one, looking only at the bonds. Because I've told you there are two concepts behind this. So this concept that I presented is looking at polarity because of the bonds. Okay? So that's the first one. So may I cut the video first.